Okay, we're now on page 16. We're finishing up this section on growth and decay. Going to finish the last 2 pages of the notes. Newton's law of cooling. And again, this is an exponential function, again, with a constant that's being added to it. But k is less than 0. Heated things decrease exponentially over time, and they end up at the temperature of the room or wherever they're sitting, in a refrigerator or whatever, outside. That's the lowest it can go to. The things can't cool any more than that. So here's the formula. The final temperature is equal to all of this. So let's see what these things represent. U of T is the ending temperature at time equal to T, however many hours or minutes or seconds or whatever. Capital T is the ambient temperature, the temperature that's around everywhere. And typically that's room temperature or the surrounding temperature, basically, of the object. U sub 0, or U naught, is the beginning temperature. So you can see where it's located. It's before the E. K is the constant, the rate of cooling, how fast it's cooling off. And T, of course, is time. Okay, so here we go. Thawing time of steak. A frozen steak has temperature of 28 degrees Fahrenheit. It is placed in a room with a constant temperature of 75 degrees. So after 10 minutes, the temperature of the steak has risen to 35 degrees Fahrenheit. So again, you see they've given you 2 times, the beginning time and an ending time, after a certain amount of time. That's the information they've given you so that you can calculate the constant that you will need in this formula. What will the temperature of the steak be after 30 minutes? And how long will it take the steak to thaw to a temperature of 45 degrees? So the first step, find K. Using the information that they give us. So we know that the temperature at time T, 10 minutes, after 10 minutes, the steak has risen to 35 degrees. So we know that this is the original, this is the formula that we're going to be using to find K. So the ending temperature for the given information to find K is 35 degrees, and it's equal to the ambient temperature, the beginning the ambient temperature of the room, which is 75 degrees. And to that, we're going to add this whole information, the constant, and so on. And this is U sub 0, that's the beginning amount, the temperature of the steak. So it's 28 degrees minus the ambient temperature times E to the 10 minutes, that's T, times K. So we have one unknown thing, and we just have to calculate it. So we're going to go 35 minus 75. Divide both sides by this, 28 minus 75. And that will equal E to the 10K. And that ends up being 40 over 47. Of course, we're going to do the ln of both sides. So we end up the ln of 40 divided by 47 equals 10K. And so K equals this. So put that into your calculator, store it. That's your constant. Now, we're ready to find the information they've asked for part A. What will the temperature be after 30 minutes? So T will equal 30. Okay, so U, the temperature after 30 minutes, is equal to 75, the ambient temperature, plus the beginning temperature of the state, minus that same 75, times E to the 30, and we've got this stored as X, so I'm just going to go ahead and just write K, because we know that K is this information. And just put it in your calculator, and you'll get 46.028 degrees after 30 minutes. And then B, I want to know, well, how long will it take to get to 45 degrees? So we know that that's the ending temperature. So it would be 45 is equal to the beginning temperature of the room plus stake temperature, same thing, times E to the, we don't know T. We do know K. It looks like a variable. It's not a variable. We know what it is. So we'll just go ahead and solve. 45 minus 75 divided by 28 minus 75, again, equals E to the T times K. ln, both sides. That's 30 over neg 47 equals K times T. Okay, both of those are negative, so this becomes a negative over a negative, and so of course we can't take the element of negative, but negative over negative is positive. So we're going to divide both sides by the constant that we know, which is K, and we'll get T. So pop that into your calculator, and you get T is equal to 27.839 minutes. These really are pretty straightforward. The steps are you find K, then you need to, and they usually give you information so that you can do that. They give you a beginning and an ending time with a given T. And so they're pretty straightforward. Another application is something that sounds pretty intimidating, but it's probably the easiest stuff we'll be doing all year. It's the logistic model. It's super easy. It's an exponential function that we can use to model situations where the growth of the dependent variable is limited, so it's not unlimited growth. So population growth, sales over product, because people, as population grows, people are dying, so it really, it's not unlimited, really. So here it is. Population after a certain amount of time is equal to C, which is the carrying capacity. It's the most that it can be, the greatest amount. And so that is the limit as T gets closer and closer to infinity of this population function, it's equal to C. So that's what that carrying capacity means. So it's an asymptote, basically. That's what it looks like. C. And so the function will do something like that. And so we can say that, the formula here is what we're really finding is the limit as T approaches infinity of this function, C, over 1 plus A times E to the negative B times T. And that is equal to C, is what they're saying. So this denominator must equal 1 because C is the numerator. So let's look at it. If you've got E to the negative BT, as T gets bigger and bigger and bigger and bigger, what's happening to this E to the negative BT? it's getting smaller and smaller and smaller, and it's approaching 0. So this amount approaches 0. And so that leaves C over 1. Because A times 0 will, of course, be 0. So that's called the carrying capacity, and it's the largest amount that it can grow. So we're going to use a graphing utility, a calculator, to graph this thing. So we'll put it in to the calculator. Clear out the first part. And we'll start with 500 divided by 1 plus 83.33 times e to the negative 0.162 t. Now we'll do zoom 6 to set the window, but really can't see much. So we know the highest it could be is how much? 500. So we want the y value to be at least 500. So we'll make it maybe 550. So let's do that. See what happens to the graph. Well, not much. You can't see much at all. So probably we don't even need the window to show any negative values, but we sure need, looks like we need a lot bigger X max. So we're going to make 100, see if that helps. And it does. Okay, so that's a classic logistic curve. If we graph the line y equals 500 in there too, which is the carrying, it's a max, you can actually see the graph approaches that. And you know, I put the window up to 550. So you should reproduce that window onto your paper. That's part A. And mark your graph with the information that you actually used on your calculator. And draw it. Also, it's important to label your window that you use, the important parts, the X-min, max, Y-min, and then Y-max was 550. That's all you really need to show on there. Starting at 0 here, label T. Okay. B. What's the carrying capacity of the environment? Well, we're going to, we know that it's going to be 500. Let's look at this. It'll be the limit. This is how you would answer the question. The limit is t approaches infinity of the function. Will equal 500 bald eagles. I didn't read the problem. It's kind of an interesting one. What we're looking for is the population of endangered species. Often environmentalists will capture an endangered species and transport him to a controlled environment where the species can produce offspring and regenerate its population. Suppose that 6 American bald eagles are captured, transported to Montana, and set free. Based on experience, the environmentalists expect the population to grow according to this model. So that's where that comes from. Okay, part C. What's the predicted population in 20 years? So we want to find the population in 20. So this will be 500 over, just using the equation, times 20. And that's a calculator activity. So when you multiply that out, you'll get 117.274 bald eagles, which of course is approximately 117. And you do this on calculator. And then part D, when will the population equal 300? So we want the time when it will be 300. And you've already got the graph. So you can actually find where it intersects 300. So go back to your calculator and type in 300 and find the intersection point. Okay, so we're looking for that intersection point. And the first curve, yes. There it is. There's the second curve. And then we're going to guess. There's only one intersection point, so it's fine. So it intersects at 29.804. You should draw a quick little sketch of what we've got on the calculator. So it goes up like that. And then we have a line at 300. And it's that intersection point that we're looking at. So it's 29.804. 300. So it will take 29.804 years. Okay, that's it. You're done.